1. The experiment that should not have worked. In science, most discoveries do not begin with surprise. They begin with confirmation. An experiment is designed not to reveal something new, but to verify what is already believed to be true. The apparatus is assembled, the variables are controlled, the outcome is predicted long before the first measurement is taken. This is how reliability is built, by proving, again and again, that reality behaves as expected. That is why this experiment was never meant to be remarkable. The conditions were ordinary by modern standards. Temperatures were controlled, noise was eliminated, external interference was reduced to levels approaching physical limits. The instruments used were not experimental prototypes, but trusted tools, devices whose behavior had been characterized for decades. Every source of uncertainty was accounted for, quantified, and minimized. According to established physical models, the result was not just predictable, it was inevitable. And yet, when the data appeared, it did not match the prediction. At first, the discrepancy was small enough to be dismissed as calibration error, small enough to be blamed on environmental fluctuation, statistical noise, or an overlooked parameter. That is how science protects itself from false discovery. No single result is trusted. An anomaly is meaningless unless it survives scrutiny. So the experiment was repeated. The same result appeared. The equipment was recalibrated. The environment was altered. The initial conditions were reset. The measurement protocol was changed. Independent teams reproduced the setup. The experiment was performed again, then again, then again. The anomaly did not disappear. It became sharper. What disturbed the researchers was not that the result violated a known law. It didn't. Conservation of energy held. Momentum was conserved. No fundamental symmetry was broken. Every foundational principle of physics remained intact. And that was precisely the problem. The universe was behaving correctly, just not intuitively. Something about the system responded in a way that contradicted what education, experience, and mental models suggested should happen. Matter behaved as if it possessed properties it should not possess. A response occurred where resistance was expected. Stability appeared where decay should dominate. Motion followed a direction opposite to applied influence. Not randomly, not intermittently, but consistently. This is the moment where scientific discomfort begins. Because when results are chaotic, science knows how to respond. When results are noisy, science improves precision. When results are contradictory, science revises models. But when results are clean, repeatable, and wrong, science must question its assumptions. The equations used to describe the system were not incorrect, but they were incomplete. They worked perfectly under most conditions, which is why they had been trusted for so long. But at certain scales, under certain constraints, those equations described only an approximation of reality. And approximations, no matter how successful, eventually fail. What made this discovery particularly unsettling was how quiet it was. There was no explosion, no dramatic visual anomaly, no obvious malfunction. The system did exactly what the mathematics allowed, but in a regime few people had explored deeply enough to feel comfortable. This is where physics becomes counterintuitive. At microscopic and quantum scales, matter does not behave as solid objects do in daily life. It does not occupy a single position. It does not respond instantaneously. It does not experience barriers as absolute. Instead, matter is governed by probability distributions, wave functions, and boundary conditions that allow behavior forbidden in classical experience but permitted by physical law. The experiment revealed one of these regimes. What appeared to be a violation was actually a demonstration of a deeper rule, one that had always existed in the equations, but had been ignored because it felt unreasonable. The mathematics allowed it. The universe obeyed it. Humans simply hadn't internalized it. And that gap between what physics permits and what intuition accepts is where the story begins. Because once scientists confirmed that this behavior was not an error, a new realization followed quickly and uncomfortably. If matter can behave this way under controlled conditions, then similar effects may already be shaping technologies we rely on quietly, invisibly, without public awareness. This was not a breakthrough announced to the world. It was a recalibration of understanding that unfolded slowly, through papers, replication, and cautious language. But beneath that restraint was a profound shift, the realization that the rules most people learn are not wrong, but they are incomplete snapshots of a much stranger reality. And if physics allows behavior that feels impossible, what else might already be happening, unnoticed, simply because it does not violate the equations? That question does not emerge from speculation. It emerges from measurement. And once measurement confirms it, the discomfort never fully goes away. Because science does not promise comfort, it promises accuracy. And sometimes, accuracy reveals a universe that works perfectly, just not the way humans expected it to. 2. The rules we thought were absolute. To understand why the experiment felt so unsettling, it is necessary to understand the rules scientists believed they were testing, not the equations written in textbooks, but the deeper assumptions that shaped how generations learned to think about the physical world. Physics, at its core, is not just a collection of formulas. It is a framework for intuition. Long before students encounter quantum mechanics or advanced theory, they are taught a simpler version of reality, one that aligns with everyday experience. Objects have clear boundaries, causes precede effects. Barriers block motion, systems lose energy and move toward disorder. These principles are not presented as conveniences, but as truths, and for most of human history, they worked extraordinarily well. Classical physics emerged from direct observation. It was built by watching planets move, projectiles arc, and objects collide. The rules it produced were powerful because they matched the scale at which humans live. At those scales, matter behaves predictably, forces respond proportionally, time flows uniformly, nothing passes through walls, nothing moves without resistance. These ideas became so reliable that they were treated as absolutes. But science has always known quietly that these rules were approximations. Even Isaac Newton understood that his laws described behavior under specific conditions, not all conditions. What made classical physics dominant was not its completeness, but its accuracy within a narrow domain. The problem is that success breeds confidence. As technology advanced, instruments became more precise, experiments became more controlled, and predictions became more accurate. The rules continued to hold until they didn't. But when they failed, the failure was subtle. It did not announce itself as a contradiction. It appeared as a deviation at the edge of measurement, easy to ignore. This is how assumptions become invisible. By the 20th century, physics had already discovered that reality behaves differently at extreme scales. Quantum mechanics revealed particles behaving as waves. Relativity showed time bending and space contracting. But these ideas were compartmentalized. They were treated as special cases, important, but separate from the real world governed by classical intuition. Everyday reasoning remained classical. What most people and even many scientists internalized was a layered view of reality. At small scales, strange things happen. At large scales, the rules return to normal. The universe was odd but contained, predictable where it mattered. That belief provided comfort. It meant that the counterintuitive aspects of physics could remain abstract, mathematical, safely distant from daily life. Quantum weirdness belonged in equations and laboratories, not in materials, devices, or environments people interact with. The experiment described earlier disrupted this separation. It showed that behaviors once thought confined to extreme or theoretical domains could emerge under controlled, engineered conditions, not because nature changed but because humans learned how to access regimes of physics previously unreachable. This is the moment where the concept of rules begins to fracture. In physics, a rule is not a command. It is a description of patterns observed under certain constraints. Change the constraints, and the pattern changes. The universe does not care which version humans find intuitive. What made this realization difficult was not that physics allowed the behavior, but that human mental models did not. Education simplifies. It must. Teaching the full complexity of physical reality up front would paralyze learning. But simplification carries a hidden cost. Students internalize models as truths, not as tools. Over time, those tools hardened into beliefs. The experiment forced scientists to confront this distinction. The laws had not failed. The assumptions about their universality had. And once that door opened, a deeper unease followed. If these rules were not absolute, then the boundary between possible and impossible was no longer fixed. It became conditional, context-dependent, engineering-dependent. That realization shifts science from discovery to design. Because if behavior depends on structure, scale, and constraints, then creating the right conditions can produce outcomes that feel impossible while remaining fully lawful. This is not rule-breaking. It is rule-revealing. And it raises a critical question that will shape everything that follows in this documentary. If the rules humans trust are only approximations, how many other impossible behaviors are simply waiting for the right conditions to emerge? That question does not threaten physics. It expands it. And once it is asked, there is no returning to the comfort of absolutes, because the universe was never constrained by human intuition. It only appeared that way until measurement proved otherwise. When the math refused to agree with intuition, long before the experiment produced its unsettling result, the warning signs were already present, quietly embedded in the mathematics, not as errors, not as contradictions, but as solutions no one wanted to take seriously. In physics, equations do not describe how the world should behave. They describe how it can behave. Every valid solution to an equation represents a physically allowed outcome, even if that outcome feels absurd. And this is where discomfort begins, because mathematics is indifferent to human intuition. For decades, physicists had encountered solutions that seemed wrong, negative values where only positive ones made sense, oscillations that refused to decay, probabilities that leaked across forbidden boundaries. These results were often treated as mathematical artifacts useful for calculations, but not to be interpreted literally. Not because they were incorrect, but because they felt unreasonable. Consider how most people think about motion. Apply a force, and an object accelerates in the direction of that force. This intuition is so deeply embedded that it feels inseparable from reality itself. But in certain equations describing collective particle behavior, the math allows something strange: acceleration opposite to the applied force, a system that moves against influence. For a long time, such results were ignored or reinterpreted, not because they violated physics, but because no known material could display such behavior under accessible conditions. The math was ahead of reality. The same pattern appeared in quantum theory, when early equations suggested particles could exist in multiple states simultaneously or pass through barriers without crossing them. These ideas were treated as probabilistic bookkeeping, useful for predictions, but not descriptions of physical behavior. Even time itself became suspect. The equations describing periodically driven quantum systems allowed for stable oscillations that did not dissipate energy structures, that repeated in time the way crystals repeat in space. For years, these solutions remained theoretical curiosities, interesting, but disconnected from the physical world. The mathematics permitted them. The intuition rejected them. This tension between math and meaning is not new. Every major advance in physics has passed through it. What made this moment different was that the equations were no longer waiting for interpretation, they were being realized experimentally. As computational power increased, scientists began simulating systems at scales and complexities previously unreachable. These simulations did not simplify intuition, they challenged it. They showed that when particles interact collectively, new behaviors emerge that cannot be predicted by studying components in isolation. Emergence is where intuition breaks. A single atom behaves predictably. A collection of atoms can behave in ways no individual atom ever could. The equations describing such systems do not merely scale, they transform. New terms dominate. Old assumptions collapse. The mathematics began insisting on outcomes that felt alien: negative effective mass, persistent temporal order, non-zero probability in forbidden regions. Each of these emerged not as theoretical provocations, but as stable solutions under specific constraints. What unsettled scientists was not that these behaviors existed in equations, but that they refused to disappear when conditions were made more realistic, when approximations were removed, when noise was added, when simulations included imperfections. The math kept returning the same answer. This is the moment where denial becomes impossible. In physics, if an equation repeatedly predicts a phenomenon across independent models, something must give. Either the mathematics is wrong or human interpretation is incomplete. And mathematics, built on symmetry and consistency, rarely fails without warning. So physicists did what they always do when intuition collapses. They stopped arguing with the equations and started asking what kind of reality would allow them to be true. This shift marks a critical transition in the story. Up to this point, strange behaviors were theoretical allowances, possibilities in abstract spaces. But now, guided by mathematics, scientists began designing experiments not to confirm expectations, but to invite the impossible. They asked different questions. What if mass is not always resistance, but sometimes response? What if barriers are statistical, not absolute? What if equilibrium does not always mean stillness? These questions did not emerge from imagination. They emerged from equations that refused to be ignored. And when the experiments finally caught up to the math, the results were not dramatic, they were precise, quiet, reproducible, exactly what the equations predicted. This is when physics becomes uncomfortable for a different reason. Because mathematics had not predicted chaos. It had predicted order, just not the kind humans were prepared to recognize. The universe, it seemed, was not breaking rules. It was following rules humans had never truly understood. And that realization carries a subtle threat. If mathematics can describe behaviors humans cannot intuit, then understanding reality requires surrendering intuition itself. Trust shifts from experience to abstraction, from what feels reasonable to what survives calculation. This is not a failure of science. It is its most honest moment. Because the universe has never been obligated to make sense to human perception. It only needs to be consistent. And consistency, when revealed by mathematics, can be far more unsettling than mystery. In the next section, this tension resolves into something tangible because these equations did not remain on paper. They began to shape matter itself. And when structure proved more powerful than substance, the implications became impossible to ignore. 4. Matter that moves the wrong way. To appreciate why negative mass unsettled physicists so deeply, it is important to understand what mass actually represents in physics, not as a number, but as a relationship. In classical mechanics, mass is resistance. It is the measure of how strongly an object opposes changes to its motion. Apply a force, and mass determines how much acceleration follows. This relationship is so intuitive that it feels inseparable from reality itself. Heavy objects respond slowly. Light objects respond quickly. The direction of acceleration always follows the direction of force. This intuition is not just educational, it is neurological. Human brains evolved in environments where this relationship never failed. Every interaction reinforced it. Over time, mass became synonymous with inertia, stability, and predictability. But physics does not define mass by intuition. It defines mass mathematically. And mathematically, mass is not an intrinsic thing. It is a parameter that emerges from how a system stores and exchanges energy. Under most conditions, that parameter is positive, but the equations never require it to be. The possibility of negative effective mass had existed quietly in theoretical physics for decades. It appeared in dispersion relations, band structures, and collective excitation models, always as a legitimate solution, always carefully avoided in interpretation. Why? Because no known system could realize it until technology made it possible to control matter at unprecedented levels of precision. The breakthrough came when scientists stopped treating particles as isolated objects and began treating them as participants in an energy landscape. In such landscapes, motion is not dictated solely by applied force, but by how the system's internal structure redistributes that force. Imagine a ball rolling on a surface. If the surface slopes downward, the ball accelerates forward. But if the surface is shaped so that energy decreases in the opposite direction, the same push produces motion that feels backward. The ball obeys physics perfectly. It simply follows the energy gradient, not human expectation. At quantum and condensed matter scales, particles do not move through empty space. They move through structured environments, fields, lattices, potentials engineered with extraordinary precision. In these environments, energy landscapes can be shaped deliberately. This is where negative mass becomes physical. In ultra-cold atomic systems, atoms are arranged in optical lattices, periodic structures formed by intersecting laser beams. These lattices do not trap atoms rigidly. They create repeating energy wells that atoms occupy as quantum waves rather than classical particles. Within this framework, motion is governed by a relationship between energy and momentum known as a dispersion relation. Under normal conditions, this relationship produces positive curvature, force and acceleration align. But if the curvature inverts, acceleration reverses. This inversion does not require exotic particles. It requires structure. By tuning laser intensity, spacing, and interaction strength, scientists reshaped the energy landscape itself. The atoms responded accordingly. Apply a force and the collective state accelerates opposite to that force. This behavior is not symbolic. It is measured directly. Velocity shifts in the wrong direction. Momentum distributions confirm inversion. Independent measurements agree. The effect persists as long as the engineered conditions remain intact. No law is broken. Energy is conserved because the system's internal configuration absorbs and redistributes work. Momentum is conserved across the entire system, including fields and constraints. The universe remains perfectly balanced. What changes is interpretation. Mass, once treated as an absolute property, reveals itself as a contextual response. In engineered systems, inertia can be reversed not by negating matter, but by redefining how motion emerges. This realization forced a profound shift in materials science. If response can be engineered independently of composition, then materials are no longer passive. They become behavioral systems. Their function depends less on what they are made of, and more on how they are organized in space, time, and interaction. This is the foundation of a new class of technologies. Negative mass systems are being explored for vibration suppression, where disturbances are actively cancelled rather than absorbed. In precision measurement, they allow sensitivity beyond classical limits by amplifying desired signals, while suppressing noise. In quantum systems, they enable stable configurations that would otherwise collapse. What is most unsettling is not their usefulness but their predictability. Once the framework is understood, these effects are not surprising. They are inevitable. The mathematics demands them. The engineering realizes them, which raises an uncomfortable implication. If such a fundamental concept as mass can reverse its behavioral meaning under the right conditions, then many other fixed properties may also be conditional. Stability, resistance, equilibrium, even causality, under certain interpretations, becomes less rigid than intuition suggests. Negative mass is not a curiosity. It is a warning. It signals that the physical world is far more flexible than human intuition ever prepared us for. That reality is governed not by simple rules, but by layered conditions, rules within rules, behaviors within structures. And once scientists learn to design these conditions deliberately, the question stopped being what is possible. It became what is inevitable, because if matter can be persuaded to respond against force, what happens when similar principles are applied to time itself? In the next section, that question stops being hypothetical when scientists encounter systems that refuse to decay, oscillations that persist without energy loss, and the discovery that time, like space, can be structured. Section 5. When matter refuses to stay put. By every rule we teach, matter is supposed to behave. It occupies space. It resists intrusion. It cannot simply appear where it is not. From childhood onward, this expectation becomes instinct. You do not expect your hand to pass through a wall. You do not expect an object to escape a sealed container without breaking it. And for centuries, physics reinforced this intuition with equations that worked astonishingly well. At human scales, matter was solid, location was fixed, and barriers meant boundaries. But deep beneath those familiar assumptions, something else was quietly happening, something that did not announce itself with explosions or paradoxes, but with statistics, probabilities, and patient repetition. Quantum tunneling was not discovered because scientists were searching for miracles. It was uncovered because equations that described atomic behavior refused to balance unless particles were allowed to do something impossible. Electrons confined in atoms should not have had enough energy to remain bound, yet they did. Nuclear reactions inside stars should not have occurred at the observed rates, yet they did. Alpha particles emitted from radioactive elements should have remained trapped inside nuclei, yet they escaped. The mathematics demanded a solution that intuition rejected. Particles were passing through barriers they did not have the energy to overcome, not by breaking them, not by weakening them, but by ignoring them. This was not metaphor. It was measurement. When researchers built potential barriers in laboratories, regions of space, where classical physics forbade passage and sent particles toward them, a fraction appeared on the other side, not occasionally, not unpredictably, but with precise probabilities that matched the equations exactly. Increase the barrier width, and fewer particles made it through. Increase the barrier height, and the probability dropped exponentially. Nothing about the process was chaotic. It was structured, repeatable, and brutally consistent. Reality was not misbehaving. It was obeying a deeper rule set. The key realization was that at quantum scales, particles are not points. They are described by wave functions, mathematical objects that spread across space, encoding probabilities rather than certainties. When a particle encounters a barrier, its wave function does not stop abruptly. It decays smoothly inside the forbidden region, leaking into the space beyond. If the barrier is thin enough, the decaying wave still has non-zero amplitude on the far side. And when a measurement is made, the particle may be found there having traversed a region where, according to classical logic, it could not exist. This does not mean the particle decides to cheat. It does not mean it borrows energy from the future or sneaks through hidden cracks. It means that the concept of location itself is different at fundamental scales. The universe does not track particles as objects moving along paths. It tracks probability distributions evolving according to precise mathematical laws. Tunneling is not an exception to physics. It is physics, operating without regard for human intuition. What makes this phenomenon unsettling is not just that it happens, but that everything around us depends on it. The sun shines because quantum tunneling allows hydrogen nuclei to fuse at temperatures that would otherwise be too low. Without tunneling, stars would not ignite, galaxies would remain dark, and life would never emerge. The solid-state electronics that define modern civilization, transistors, semiconductors, microprocessors, rely on electrons tunneling through engineered barriers billions of times per second. Every calculation, every image, every transmission you see, it exists because matter does not fully respect confinement. And yet, despite its ubiquity, tunneling remains invisible at human scales. A baseball will never tunnel through a wall not because the laws forbid it, but because the probabilities are so astronomically small that the universe would need more time than it has existed for it to happen once. The same equations apply. The difference is scale. At the level of atoms, probabilities matter. At the level of people, they vanish into insignificance. Reality does not change its rules, it changes their consequences. This introduces a disturbing implication. The boundaries we perceive, the solidity of objects, the permanence of separation, are not absolute features of the universe. They are emergent behaviors, arising from overwhelming statistical suppression. The wall feels solid not because it is fundamentally impenetrable, but because the probability of penetration is effectively zero. Effectively, but not philosophically. At its core, matter is less rigid than it appears, more permissive than we expect, and far less concerned with human categories of possible and impossible. As experiments refined, tunneling revealed deeper layers. In scanning tunneling microscopes, scientists exploited this effect to image individual atoms not by touching them, but by measuring how electrons tunnel across tiny gaps. The closer the probe comes to a surface, the greater the tunneling current. This relationship is so sensitive that it can detect changes smaller than the diameter of a single atom. We did not just accept tunneling, we turned it into vision. We learned to see the structure of reality by watching particles violate our expectations. But with this power came a philosophical shift that could not be undone. If particles can exist on both sides of a barrier until measured, then barriers are not absolute divisions. They are gradients, thresholds, regions where certainty fades rather than stops. The universe, at its foundation, does not enforce sharp lines. It enforces smooth transitions, governed by equations that care nothing for comfort or common sense. This realization quietly erodes the classical worldview. It suggests that the universe is not built from objects interacting across space, but from mathematical structures evolving through possibility. What we call matter is stabilized probability. What we call motion is the reshaping of likelihood, and what we call impossibility is often just improbability taken to an extreme. Quantum tunneling does not announce itself with spectacle. It operates beneath perception, beneath awareness, beneath belief. But once understood, it leaves nothing untouched. It tells us that containment is conditional, separation is statistical, and the universe is far less rigid than it appears. The walls we trust are not enforced by absolute law. They are upheld by numbers vast, merciless and usually reliable. Usually. And if matter can cross forbidden regions without crossing them in the way we understand crossing, then the question is no longer whether reality follows rules. The question is whose intuition those rules were ever meant to satisfy. Section 6. When pushing forward makes things fall backward. There is a rule so deeply embedded in human experience that it feels beyond question. If you push something, it moves in the direction you push it. This expectation is older than language, older than mathematics. It is learned before thought. Force produces acceleration. Cause produces effect. From Newton onward, physics did not challenge this intuition, it formalized it. Mass resisted acceleration, but never reversed it. The heavier the object, the harder it was to move. But it always moved forward, until it didn't. The first hints that this rule might fail did not come from speculative theory, but from carefully controlled experiments in solid-state physics. Researchers studying electrons inside crystals began noticing something unsettling. Under certain conditions, when external force was applied, the particles accelerated in the opposite direction, not metaphorically, not temporarily, measurably, reproducibly. According to every classical expectation, this should have been impossible. Yet the equations describing the system did not break. Energy was conserved. Momentum was conserved. No physical law was violated. What failed was intuition. The concept that emerged was called negative effective mass. Not negative mass in the science fiction sense, no exotic matter falling upward through space, but something more subtle and more disturbing. In complex systems, particularly those governed by quantum mechanics, mass is not always a fixed, intrinsic property. It can emerge from how particles interact with their environment. In crystalline solids, electrons do not move freely. They are constrained by periodic atomic lattices, forced to respond to repeating electric fields that reshape their behavior. The electron becomes something new, a quasi-particle, carrying modified properties that reflect the structure it inhabits. In this environment, mass becomes a relationship, not a substance. When physicists examined the energy-momentum curves of these systems, they found regions where the curvature inverted. In these regions, applying a force caused acceleration opposite to the force direction. The equations did not suggest resistance. They suggested inversion. The particle was not refusing to move. It was responding exactly as dictated, just not in the way common sense expected. This is not semantic trickery. Negative effective mass produces real, observable consequences. In laboratory systems such as ultra-cold atomic gases, researchers have engineered conditions where entire clouds of atoms behave as if they possess negative mass. Push them, and they move toward you. Pull them, and they move away. Stability emerges not from balance, but from mutual opposition. Systems that should explode remain coherent. Motion that should amplify cancels itself out. What makes this phenomenon unsettling is not that it is rare, but that it is precise. These systems are predictable. Their behavior is not chaotic or pathological. It is mathematically clean. The same equations that govern satellites and pendulums, when extended into quantum regimes, allow this inversion naturally. The universe does not resist the idea of negative effective mass. It accommodates it quietly, wherever structure and constraint reshape motion. This forces a reevaluation of what mass actually means. In everyday language, mass feels fundamental, how much stuff something contains. But physics reveals something more abstract. Mass is a measure of how a system responds to force. Change the rules of response, and mass changes with them. In extreme conditions, it can even reverse sign without contradiction. Negative effective mass does not allow perpetual motion. It does not break thermodynamics. Energy still has a cost. Entropy still increases. But it does change stability. Systems with both positive and negative effective mass can lock into self-regulating motion, where disturbances cancel instead of amplify. This is not hypothetical. It is actively studied in quantum simulators and condensed matter experiments. Engineers are exploring whether such principles could lead to ultra-stable materials, frictionless transport, or new forms of energy control. Yet the deeper implication is philosophical. If mass, one of the most basic quantities in physics, is not absolute, then neither is our intuition about motion, resistance, or causality. The universe does not guarantee that effort aligns with outcome. It guarantees only that equations remain consistent. Direction is not privileged. Response is contextual. This realization echoes backward through history. Newton's laws were never wrong. They were incomplete valid within a domain where effective mass remains positive and constant. Outside that domain, the same logical framework yields unfamiliar behavior. The universe did not change. Our vantage point did. Negative effective mass also intersects with gravity in subtle ways. In cosmology, effective negative pressure plays a role in explaining cosmic expansion. While not the same phenomenon, the conceptual bridge is unavoidable. Under certain conditions, systems respond to force by amplifying separation rather than resisting it. Attraction can behave like repulsion. Stability can arise from opposition. The universe is comfortable operating in regimes that feel backward to us. And once this door is opened, it does not close neatly. If matter can tunnel through barriers without crossing them, and if mass can respond oppositely to force without violating physics, then the classical picture of a universe built from solid objects obeying intuitive rules begins to dissolve. What replaces it is not chaos, but structure deeper, stranger, and less concerned with how reality feels to human observers. Negative effective mass does not announce a broken universe. It announces a layered one, a reality where behavior depends not just on what something is, but on where it is embedded, how it is constrained, and which mathematical relationships are allowed to dominate. And this raises an unavoidable question. If the most fundamental properties of matter are not fixed, but emergent, if direction, resistance, and stability can invert under the right conditions, then what else do we assume is absolute simply because we have never pushed reality far enough to watch it respond differently? When you are ready, Section 7 can escalate this tension further by introducing time crystal systems that break time translation, symmetry, move without energy loss, and challenge the assumption that motion requires change while remaining fully compliant with thermodynamics and quantum law. Section 7. When time itself refused to flow normally. If negative effective mass unsettled the idea that force and motion must agree, the next discovery unsettled something even more fundamental, the assumption that time itself always moves forward in the same way for every system. Not the arrow of time in philosophy, not time travel, something quieter and far more precise. A system that moved, yet did not progress. A pattern that repeated forever without wearing out. A structure that evolved in time while refusing to decay. At first, the idea sounded like a mistake in language. Physics had long accepted that crystals break symmetry in space. A crystal repeats itself. Its atoms are arranged in a pattern that looks the same at regular intervals. That repetition defines solidity. But time, by contrast, was treated as inviolable. The laws of physics are symmetric in time, but physical systems are not. Motion dissipates, oscillations dampen, energy spreads out, entropy increases. A clock ticks because something changes and because it cannot tick forever without energy loss, until a proposal appeared that suggested otherwise. In 2012, physicist Frank Wilczek asked a question that many initially dismissed as ill-posed. Could a system exist that breaks time translation symmetry the way a crystal breaks spatial symmetry? In other words, could there be a structure that repeats itself not in space, but in time, cycling endlessly without consuming energy? The immediate reaction from the scientific community was skepticism. It sounded like a perpetual motion machine in disguise. Thermodynamics seemed to forbid it, but the equations did not collapse. What followed was not instant validation, but years of refinement. Physicists realized that the original idea needed constraints. The system could not be continuously driven. It could not extract work, but under the right quantum conditions, especially in many-body systems subjected to periodic driving, something remarkable could emerge, a state that oscillated with a fixed rhythm, even though the driving force itself was irregular or at a different frequency. The system responded not by syncing, but by resisting synchronization, locking into its own temporal pattern. This was the birth of a time crystal. Unlike ordinary oscillations, time crystals do not gradually lose energy. Their motion is not powered by consumption, but by structure. Quantum entanglement and disorder work together to prevent thermalization. The system does not settle into equilibrium. It does not smear out its energy. Instead, it remembers. Every cycle reinforces the next. The system moves through time without aging in the usual sense. This is not metaphor. Time crystals have been built in laboratory experiments using trapped ions, superconducting qubits, and ultra-cold atoms. Researchers observed stable, repeating temporal patterns that persisted indefinitely under observation. The systems were measured again and again, and the rhythm remained unchanged. No energy was extracted, no law was broken. Entropy still increased globally, but locally something astonishing occurred. A pocket of matter refused to forget its past. What makes time crystals disturbing is not their motion, but their defiance of expectation. We assume that change implies cost, that persistence implies fuel, that stability requires stasis. Time crystals violate all three intuitions simultaneously. They are dynamic, stable, and non-dissipative. They exist only because quantum mechanics allows correlations to lock time the way lattices lock space. This forces a reconsideration of what motion means. In classical thinking, motion is something that happens to matter. In time crystals, motion is something matter is. The system's identity includes its rhythm. Remove the oscillation, and the system ceases to be what it is. Time becomes a structural dimension, not just a backdrop. The implications extend far beyond novelty. Time crystals offer insight into how information can be preserved in noisy environments, an essential challenge for quantum computing. They suggest mechanisms by which coherence can survive in systems that should decohere. They hint that temporal order can be engineered, not merely observed. Just as metamaterials allowed engineers to shape space for waves, time crystals suggest the possibility of shaping time for processes. Yet this possibility arrives with a philosophical cost. If systems can move forever without progressing, then the assumption that time and change are inseparable collapses. The arrow of time remains globally intact, but locally it can bend, stall, or loop without contradiction. The universe does not require everything to age at the same conceptual rate. It allows islands of persistent structures that live in rhythm rather than trajectory. This reframes how we understand decay, memory, and stability. Perhaps some systems do not survive by resisting change, but by organizing it. Perhaps endurance is not the absence of motion, but the perfection of it. Time crystals do not suggest that time is broken. They suggest it is more flexible than intuition allows, that under the right constraints, reality can support patterns that feel impossible only because everyday matter cannot sustain them. And this realization leads to a deeper unease. If time can be structured, and mass can invert its response to force, then the classical picture of a universe marching uniformly forward, objects resisting motion, systems relaxing into rest, no longer applies universally. Reality is not just governed by laws. It is shaped by architectures, by patterns that decide which rules dominate and which fade into irrelevance. Once matter learns to remember time, the question is no longer whether physics allows such behavior. The question becomes where else it might already be happening quietly, precisely, and far outside the range of human intuition. Section 8. The barrier that was never absolute. By the time physicists accepted that time itself could organize into stable structures. Another assumption had already been quietly eroding, one so fundamental that it shaped how humans understood walls, limits, and separation itself. The belief was simple and comforting. If something does not have enough energy to cross a barrier, it will not cross. A ball cannot pass through a wall. A particle cannot escape a well without climbing out. Reality, it seemed, respected borders. Quantum mechanics never did. From its earliest days, the equations hinted at something deeply counterintuitive. They suggested that particles are not points, but probabilities, that location is not a fact, but a distribution, and that barriers, no matter how solid they appear, are never perfectly sealed. At first, this was treated as a mathematical oddity, an artifact of wave equations applied to subatomic scales, something strange, but safely confined to the microscopic world. That assumption did not survive experimentation. Quantum tunneling was not discovered through philosophical speculation, but through precise, repeatable measurements. Electrons were observed passing through energy barriers they did not have the energy to overcome. Not by cheating, not by borrowing energy, simply by existing as waves that extended beyond the forbidden region. The math was unforgiving. There was a non-zero probability that the particle would appear on the other side. And it did. At first, tunneling was treated as negligible, something relevant only in nuclear reactions and radioactive decay. But then it became clear that without tunneling, the sun could not shine. Nuclear fusion in stars relies on particles tunneling through repulsive forces that should keep them apart. Life on Earth exists because barriers were never absolute to begin with. This realization reframed the concept of impossibility. In the quantum world, cannot does not mean zero, it means unlikely. And when systems repeat interactions trillions of times, unlikely becomes inevitable. Barriers stop being walls and start becoming filters, structures that shape probability rather than prohibit motion. What changed everything was scale. As experimental control improved, physicists began observing tunneling not just in isolated particles, but in collective systems. Superconductors allow electrons to tunnel coherently across insulating gaps. Joseon junctions exploit tunneling to create ultra-precise oscillations used in quantum measurement. Scanning tunneling microscopes use tunneling itself to image individual atoms by measuring the probability of electrons appearing where they should not be. Reality was no longer respecting edges, it was negotiating them. Then came the unsettling question: if tunneling is allowed for particles, could it ever matter for larger systems? Not whole objects passing through walls, that remains astronomically unlikely, but behavior shaped by tunneling at macroscopic scales. The answer, slowly and carefully, became yes. Chemical reactions depend on tunneling. Biological enzymes rely on it to speed up life-critical processes. Even smell, according to some theories, may involve quantum tunneling of electrons responding to molecular vibrations. The barrier between physics and biology quietly dissolved not by force, but by probability. This forces a shift in worldview. Classical intuition treats barriers as binary, pass or fail. Quantum reality treats them as gradients. Nothing is ever perfectly confined. Nothing is ever perfectly isolated. Every boundary leaks not dramatically, but persistently. Given enough time, even the most forbidden transition leaves a trace. The discomfort comes from what this implies about control. If systems can cross barriers without crossing them, then containment is no longer absolute. Isolation becomes an approximation. Security becomes statistical. The universe does not promise prevention, only suppression. And suppression depends on scale, structure, and patience. This is not chaos. It is precision taken to its extreme. Quantum tunneling does not allow randomness to dominate reality. It allows rare events to matter. It ensures that the universe is never fully locked into place, that no configuration is final, that every structure, no matter how rigid, contains the possibility of change, not because laws are broken, but because they are followed too closely. When combined with time crystals and negative effective mass, a pattern emerges. Matter can move without progressing. Matter can respond opposite to force. Matter can cross barriers without crossing them. Each phenomenon obeys physics perfectly and yet violates the story humans tell themselves about how reality should behave. The laws remain intact. Intuition does not. And this leads to a deeper realization. The universe is not built around human-scale certainty. It is built around probabilities that become meaningful only across vast repetitions. What appears solid, fixed, and inviolable is often just a temporary statistical convenience. Stability is not guaranteed, it is negotiated moment by moment. Once barriers stop being absolute, the idea of control must be redefined. Not as domination, but as influence. Not as prevention, but as probability shaping. The future is no longer blocked by walls, it is guided by likelihoods, and that realization prepares us for the next escalation, because if matter can tunnel through barriers, and time can crystallize into rhythm, then the next question is unavoidable. What happens when these principles are engineered together, when probability, time, and structure are deliberately aligned to produce behaviors that feel indistinguishable from defying reality itself? Section 9. The scientists who hesitated. At this stage, it becomes tempting to frame the story as technology versus humanity, or progress versus ethics, but that framing is too simple and dangerously misleading, because the truth is quieter, heavier, and far more human. The people closest to these discoveries were not reckless, they were not blind, and they were not unaware of the implications unfolding around them. In fact, the most striking pattern across laboratories, research papers, and private correspondence was not excitement but hesitation. Physicists are trained to doubt results, but they are also trained to doubt themselves. When matter begins behaving in ways that undermine intuition, the first response is not celebration. It is restraint, a slowing down, a careful rereading of assumptions that had always been safe to ignore. Behind every paper describing tunneling systems, time periodic matter, or negative effective mass, there were months, sometimes years, of internal debate, conversations that never made it into journals, questions that could not be peer-reviewed because they were not technical, but philosophical. Just because something can be done, should it be explored further? Just because a system is allowed by physics, should it be engineered? Just because control is possible, does that imply responsibility? These questions have no equations. For decades, physics progressed by observing what already existed. Scientists studied stars, atoms, forces, things that revealed themselves without intervention. But now, the role had shifted. These systems did not exist naturally at scale. They had to be constructed, maintained, stabilized, repeated. That difference matters. When you observe nature, you are accountable only for understanding. When you engineer new regimes of behavior, you become accountable for consequences, many of which cannot be predicted. This created a subtle but profound psychological burden. Researchers working on time crystals spoke openly about the discomfort of stabilizing motion that never relaxes. Engineers manipulating tunneling probabilities expressed unease about systems that bypass constraints rather than overcoming them. Materials scientists designing structures that redirect waves worried not about misuse, but about normalization. Because once a phenomenon becomes reliable, it stops feeling strange, and once it stops feeling strange, it stops feeling dangerous. The history of science offers a cautionary pattern. Most transformative technologies were not recognized as transformative at the moment they crossed the line. Nuclear physics did not feel existential until it was too late. Digital computation did not feel societal until it was ubiquitous. Algorithms did not feel behavioral until they were unavoidable. The same pattern was emerging here. Each experiment was modest in isolation, a controlled system, a specialized application, a proof of concept, but collectively, they formed a new relationship between humans and physical law, not one of obedience, but of negotiation. And negotiation implies leverage. Some scientists began to speak about the shift in careful language. They avoided public alarm, but privately acknowledged that something fundamental had changed. Physics was no longer just revealing how reality behaves, it was offering choices about which behaviors to privilege. That is an unprecedented position. When barriers are probabilistic, not absolute, then exclusion becomes design-dependent. When time can be structured, persistence becomes a variable. When mass responds oppositely to force, resistance becomes programmable. None of this violates physics, but all of it challenges the idea that physics is neutral. Neutrality was easier to assume when laws were immutable and outcomes were fixed. But when laws permit a spectrum of behaviors, and humans select which behaviors to amplify, neutrality dissolves quietly. This is where many scientists paused. Not because they feared catastrophe, but because they recognized responsibility without precedent. The ability to shape reality at this level is not inherently destructive, but it is inherently directional. Every design choice excludes alternatives. Every optimization embeds values, even unintentionally, and values, unlike equations, cannot be experimentally verified. What makes this moment unique is that no single individual or institution controls it. These discoveries are distributed across countries, disciplines, and motivations. There is no switch to turn off, no authority to consult, no clear moment of consent. Progress continues not recklessly, but inevitably, and that inevitability creates a new kind of anxiety. Not fear of misuse, but fear of normalization. The fear that systems which subtly bypass limits will become so integrated that society forgets limits ever existed. The scientists understood this before anyone else. They saw that the danger was not that physics allows these behaviors, but that humans might stop asking what they are for. That capability might outrun reflection. That wonder might fade into utility before wisdom has time to catch up. This is not a story of villains crossing lines. It is a story of careful people realizing that the line itself was never part of nature, it was part of human comfort. And comfort, once disrupted, does not easily return, which leads to the final realization. If the laws of physics never promised absolutes, only permissions, then the responsibility for meaning does not lie in the universe. It lies with us. Section 10. A universe that never promised to make sense. At the end of every scientific revolution, there is a moment that is rarely documented, not a discovery, not a breakthrough, but a quiet realization, one that does not belong to equations, papers, or conferences. It belongs to the people who must live with what has been learned. By now, it is no longer shocking that physics allows matter to tunnel through barriers, time to organize into repeating structures, or systems to behave opposite to force. Those facts have settled. They have been measured, verified, and accepted. The mathematics is stable. The experiments are repeatable. What remains unstable is meaning. For centuries, humans assumed that the universe enforced limits, that physical law existed to constrain behavior, to prevent excess, to define what was possible and what was forbidden. The idea of laws of nature carried moral weight not because nature cared, but because humans projected certainty onto it. If something could not happen, responsibility disappeared. If something must happen, blame became irrelevant. Physics quietly removed that comfort. Modern experiments reveal a universe that does not enforce outcomes, only conditions. A universe that allows behaviors rather than dictates them. A universe that offers possibilities, not prescriptions. And when possibility replaces prohibition, responsibility does not vanish, it multiplies. Because in a probabilistic universe, outcomes are not guaranteed, they are selected. Selected by design choices, environmental constraints, incentives, and values embedded long before results become visible. This is the moment where science stops protecting humanity from itself. When barriers were absolute, ethics could be deferred to physics. When decay was inevitable, permanence was not a question. When intuition matched reality, uncertainty felt manageable. None of those assumptions survive. A barrier is now a probability gradient. Time is now a manipulable parameter. Stability is now an engineered outcome. The universe has not changed. Human position within it has. For the first time, humanity is not merely discovering reality, it is choosing which version of reality to reinforce, which behaviors to stabilize, which improbabilities to normalize, which futures to make statistically inevitable. This does not require malicious intent. It requires only optimization. Optimization favors efficiency over reflection, persistence over decay, control over ambiguity. And those preferences, once encoded into physical systems, become invisible. They stop feeling like choices and start feeling like nature. This is how the deepest shifts occur, not through dramatic violations of law, but through quiet alignment with what law allows. The unsettling truth is that physics never promised safety. Humans assumed it did. Physics never guaranteed fairness, stability, or restraint. It only promised consistency. And consistency, when combined with engineering, can produce realities that feel alien without being illegal. The universe is not broken. It is indifferent, and indifference is far more demanding than opposition, because an opposing universe would push back. An indifferent one waits to see what we do. This is where the meaning of crossing a line dissolves completely. There was no moment of transgression, because there was no boundary enforced by nature. The line existed only as a psychological comfort, an assumption that somewhere, somehow, reality would refuse cooperation. It never did. The real threshold was internal. It was crossed when humans stopped asking whether something should persist, and focused only on whether it could. When longevity became a feature. When stability became a product. When improbability became infrastructure. At that point, the future stopped being something that arrives. It became something that accumulates. And accumulation does not announce itself. It feels gradual, normal, reasonable, each step justified by the previous one, each decision defensible in isolation, until suddenly, the environment no longer reflects intention, only momentum. This is not a warning about technology. It is a warning about forgetting that physics does not supply purpose. Purpose must be chosen repeatedly, consciously, and with restraint. Not once, not globally, but continuously, because the universe will not intervene if we choose poorly. The most dangerous misunderstanding is believing that because something is allowed by physics, it is endorsed by reality. Reality does not endorse, it permits, and permission without guidance is not freedom, it is obligation. Which brings us to the final, unresolved question. If the universe has always been this flexible, if limits were always probabilistic, if certainty was always an illusion maintained by scale and habit, then the responsibility for what comes next was never external, it was always ours. The universe will continue to behave exactly as it always has, quietly, consistently, without judgment. The only uncertainty left is whether humans will learn to live inside a reality that does not protect them from their own choices. And that question does not end with this documentary, it begins after it. And last final section. At some point, the question stops being what physics allows, because physics has already answered that. What remains is something far less comfortable, what it means to live inside a universe that never promised certainty, safety, or restraint. A universe that does not enforce limits, only possibilities. For most of human history, stability felt guaranteed. Walls were solid. Time moved forward. Causes came before effects. These were not just scientific assumptions. They were psychological anchors. They made the world feel dependable. But modern physics tells a quieter truth. It tells us that stability is not a law. It is a pattern, that barriers are not absolute, only unlikely to fail, that time itself can be structured, paused, repeated, that matter can behave in ways intuition was never designed to understand. The universe did not change, our position within it did. We once believed that reality would stop us from going too far, that somewhere, some rule would push back, that nature itself would say no. It never did. Physics does not prohibit outcomes, it permits them. And when permission replaces prohibition, responsibility does not disappear, it moves. In a rigid universe, outcomes are inevitable. In a permissive one, outcomes are chosen. Not chosen all at once, not consciously, but gradually, quietly, through design decisions that feel reasonable in isolation, through systems that work too well to question, through optimization that rewards efficiency over reflection. The future did not arrive suddenly, it blended in, and adaptation felt so natural that awareness lagged behind. The most unsettling realization is not that these technologies exist, it is that the universe was always this flexible. The line we thought we crossed was never enforced by nature, it was enforced by comfort. Physics never promised meaning, it never promised safety, it never promised restraint, it promised only consistency. And consistency, when paired with human intention, can build worlds that feel permanent long before wisdom catches up. The universe will not intervene, it will not warn us, it will not stop us, it will not correct our assumptions, it will simply continue to behave exactly as it always has, quietly, indifferently, precisely, which leaves only one unanswered question. If the universe does not protect us from our choices, if reality allows more than intuition can manage, if the rules were never there to save us, then awareness is no longer optional. It is the last boundary that still exists, and whether we notice it or ignore it will shape everything that comes next.